Hello people, welcome back to my channel, TheTalk. Today we are going to continue with the chapter real numbers. It's the last topic in this chapter, so that is decimal expansion of rational numbers. Before we get into the exercise questions and the problems, let's look at few definitions and terminologies that we come across the decimal expansions. So first term says a terminating decimal number. So what is a terminating decimal number? A decimal number that has a specific end digit is called as a terminating decimal number. So whenever we divide with examples and you are having whatever quotient you get is finite, like it doesn't continue, like when the quotient is 0.16, it is meaning that you're getting a remainder is 0. So if this is the quotient, the remainder is 0. So the same, that is the meaning of terminating decimal. A non-terminating decimal number. A non-terminating decimal number, it's quite opposite for terminating decimal number, which means that it does not have an end points in its decimal digit and it keeps continuing further. That means you can't end up with a division, like the division keeps on continuing and you never get the remainder 0 to 1.2356 and it keeps on continuing 2456, it keeps on going and going. So remainder will never be 0 in this case. So that's a non-terminating decimal number. And recurring decimal number. So recurring decimal number is something where the decimal number goes on repeating. Even in this case we never get the remainder 0. So it goes on, like even you keep on continuing, you will be ending at 0.2222 and keeps on continuing with the same number. The decimal number keeps on repeating forever. So we generally show it in the form of, because 2 is repeating here, you show it in the form of a bar. Suppose the question is like 0.246, 246, 246 and it goes on repeating. So you put a bar, you instead of writing it in the same way, you can also write it as 0.246 bar. That means whatever is below the bar or the vinculum, this is called as a vinculum. So whatever number you write below the vinculum, that particular number repeats, goes on repeating in the decimal part. Non-recurring decimal number, it's quite opposite for recurring decimal number. It means that the decimal number places do not repeat forever. So 1.24567814, like there is no specific pattern for the decimals getting repeated. So now we will look at a condition to check whether a decimal number is terminating or not. So this helps us in solving the exercise questions that we will be doing further. So let's look at the condition. So I'm going to write it here, the condition. So what is the condition? We take a rational number p by q. So we know that the condition that q is not equal to 0 and both of them are co-primes. So when we find the prime factorization of the denominator, so we consider the prime factorization of the denominator always, and when you do it, it should be the factors which you are getting should in the form of powers of 2 and 5. That means you can get numerous number of factors and all of them have to be in the power of 2 and 5 only, terminating decimal number. So suppose x is a decimal expansion, okay. So x is a rational number that we considered. So then you say that that particular rational number has a decimal expansion that is terminating. We will move on to the exercise question. So I will be revisiting this theorem so many times when we solve these exercise questions. So this is exercise 1.4. The first question says, without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating decimal expansion. So we have discussed about the theorem, right? If the decimal, like if you express a rational number, let's write down the theorem on the right side. So if you're considering x as a rational number p by q, so this is a rational number, and q, when you prime factorize it, it should be in the powers of 2 power m and 5 power n upon prime factorization. So remember both of these conditions. It makes it easy to find out whether a number is terminating decimal or a non-terminating decimal. Looking at the first question, 13 upon 3125. Let us look at the prime factorization of 3125. So because it is having 5 in the ones place, it can be factorized with 5. So 5 6 are 30, you are getting 12, 5 2s are 10, 5 5s are 25, 5, 5 1s are 5, 5 2s are 10, 5 5s are 25, 5 2s are 10, 5s are 25 and 5 like this. This is nothing but 5 cube. So because we could express the denominator in the form of powers of 5, it is a terminating decimal number. So it satisfies the condition, right, of the number to be called as a terminating decimal number. Then 17 upon 8. So this is easy. 8 is nothing but 2 cube. So this also could be expressed. So I'm going to write the terminating decimal number as Tn. Okay, to make it easy, to make the notation easy. So this is also terminating decimal number. Then 64 upon 455. So if you look at the prime factorization of 455, we will start with 5 first. 5 times 9 is 45, 5 times 1, and 13 times 7 is 91. So when you express it as the prime factors, so you're getting another prime factor other than 2 and 5. So 5 was one of the prime factor, 13 and 7. So it is having prime factors other than 2 and 5. So it is not a terminating number. Okay. Then 15 upon 1600. And basically we can actually simplify this further. So 15 is being divided by 3. So 3 times. 3 5s are 15. 3 2s are 10. 5 3s are 15. 5 2s are 10. So this is like 3 upon 320. So we only have to find the prime factors of 320 now. 5 times 6 is 30. 5 times 4 and 2 divides it. 2 3s are 6, 2 2s are 4, 2 16 times, 2 8 times, and this is 2 cube. So this can be like written as 3 upon, we have 1 5 and you are having 3 2 powers. So 2 cube and 8 is also 2 cube, right? So this will be 3 upon 5 multiplied by, we have a formula 6. So both of these have the combination like 2 power m and 5 power n. So yes, this is a terminating decimal number. 15 divided by 1600 is a terminating decimal number. Now we'll look at few more questions in the exercise. 29 divided by 343. Before that we will write down the expansion also. So if x equals p of, remember these 3 points, basing on this we will consider the prime factorization. So 7 times 4, 7 times 9, so this is 7 cube. 343 is basically 7 cube. So this can be written as 29 upon 7 cube. So this, what happened, it could not be expressed in the form of 2 power n and 5 power n. So this is not a terminating decimal number. Next question, 2 cube and 5 square, we are already having this in the form of 2 power m and 5 power n. So this is definitely a terminating decimal number. And the last one, apart from 2 power m and 5 power n, you are having another number. So this is not a terminating decimal number. Even though it has 2 power m and 5 power n, even if it has another prime factor, even then you do not consider it as a terminating decimal number. So I hope you understood how to find out terminating decimal numbers now. So 6 upon 15, this is 5 times 3. And you are having another factor 3, so this is also a non-terminating decimal number. 35 upon 50, we consider the prime factorization of 50, 5 times 10, and this is 2 times 5. So yes, we got the prime factorization of the denominator in the form of 5 powers and 2 powers. So yes, this is a terminating decimal number. 17 upon 210. So 210, if we find the prime factorization of it, 5 times 4 is 20, 5 times 2 is 10, and 7 times 6 is 42, 2 times 3 is 6. So this is the prime factorization of it, as it is having factors other than 2 and 5. So this is not a terminating decimal number. So all the questions of the first topic are solved. Let's move on to the next. So the question says, write down the decimal expansion for those rational numbers in question 1 above which they have terminating decimal expansions. So just go back to the video, look whatever numbers had a terminating decimal expansions. If they had a terminating decimal expansion, they asked us what is the terminating expansion for it. So the first one was 13 upon 3125. When you divide this, it's going to get an expansion of 0.00416. That is one number. And 17 divided by 8. When you divide, let's look at the division of this. So 8 times 2, 16 minus 1. You keep adding decimals. Then you bring down 0. 8 times 1, 8. We didn't get 0 yet. So we make one more 0, bring it down. 8 times 2, 16. 4. As we didn't get 0, we add one more decimal place. Finally, 8 times 5 is 40. So we got decimal 0. So you use this division method to verify all of the terminating decimal numbers. So you consider whatever numbers were had a terminating decimal expansion and then follow the long division method to find out the exact terminating decimal number of all. So after doing, you can verify the answers from here. So 15, the third terminating decimal expansion was 15 upon 1600. This had an expansion, because this we even simplified it further, this became 3 upon 320. Upon simplification of this, we got 0.009375. So then 23 upon 2 cube and pi square. Even this was simplified to 23 upon 200. This is going to be 0.115. 6 upon 15. 2 upon pi you can simplify. So this is nothing but 0.4. This was easy. The fifth question was easy. Didn't need much steps. 35 divided by 50. You simplify it. 5 times 7 and 5 times 10. So 0.7. So all these are the terminating decimal numbers that we had in the question 1. Next question says that the following real number have decimal expansions as given below. In each case, you have to decide whether they are rational or not. If they are rational and of the form P upon Q, what can you say about the prime factors of Q? That is what is asked. You have to find out whether a number is rational or not. The first question is 43.123456789. It is a finite decimal number because it is having no dots like this and it is not having any bars on the top. So it is a rational number. Because it is finite and it is a terminating decimal number, so we have done lots of questions in number 1 and 2. That is, if let us say this is x. So to call it as terminating, if x is in the form of P upon Q, Q should be in the form of 2 power m and 5 power n. Because it is a terminating decimal number, so Q has prime factors as 2 and 5 only. So that is what they asked us to find about the prime factors of the denominator Q. So it only has prime factors as 2 and 5. So now we have seen these dots here. It means that it is a non-terminating decimal number. That means you cannot, the remainder is definitely not equal to 0 and the decimal expansion keeps on continuing. So definitely it is an irrational number and it is non-terminating because you are not getting some finite decimal places. And regarding the recurrence of decimal numbers, there is no specific pattern if you observe the decimal places. It's like 1 to 0, 1 to 0, 0, 1 to 0, 0, 0. There's no specific pattern that is observed. So this is a non-recurring decimal expansion as well. Let's look at the third question. So 43.123456789 and it has a bar on top of it. A vinculum is there. So whenever a vinculum is there, the first and the foremost thing that you can confirm is that it's a non-terminating decimal first of all, but it has like recurring decimals. It's repeating. So this set, like after 9, the next decimal number would be the 9. Like if you look at the expansion of this, it's like 1, 2, 3, 4, 5, 6, 7, 8, 9. After this again the decimal continues like 1, 2, 3, 4, 5, 6, 7, 8, 9. It keeps on continuing, so on and so forth. So that is a particular decimal expansion. Of course, remainder is not equal to 0 and it is a rational number. It is non-terminating because remainder is not in a finite decimal place. Then the factors, when you consider the factors of it, because it is non-terminating but it is a recurring decimal number because the decimal places are repeating. If you consider the factors, as it is non-terminating, it will have factors. It might have factors of 2 and 5, but it has factors apart from 2 or 5. It has factors apart from 2 and 5. So we have solved all the exercise questions of exercise 1.4. I hope you have found this video informative, like we have given all the solutions for the exercise questions. So please do subscribe to our channel, The Talk. We will be starting with a next topic in the next video. So see you in the next video. Bye-bye.